Hi learners, I'm from Sononerds, and this video is going to be on Unit 5, that sounds intense, Section 5.1, Intensity. Again. In Unit 3, we discussed the 7 parameters that can describe continuous and pulsed waves, and intensity was one of those 7 parameters. So we learned that it is one of the ways to describe a wave's strength. We also learned that it's proportional to power and then amplitude squared. Based on the formula, we can see that it is inversely related to area, but directly related to power. And due to the units used for power and area, intensity ends up with a unit of watts over an area squared. For ultrasound, it's typically centimeters squared. And then finally, that it has a range between 0.1 to 100 in our diagnostic ultrasound application. The ultrasound beam is actually a lot like a flashlight beam. So if you were to take a flashlight, shine it at a wall, you would see this really strong, intense light at the center, and then as you look towards the outside, you'll start to see the light get dimmer, which means that it's weakening or less intense. And the ultrasound beam is going to do a very similar thing. It's very intense in the center, and then starts to weaken as you go out towards the edges. And that's because we're getting more area that the light is being spread over. Therefore, it's weakening inversely related to the area that it's covering. Continuing the flashlight analogy, if we were to hold the flashlight beam on the wall for hours and hours on end, that would be continuous exposure to the light energy, very similar to continuous energy that we get from a continuous wave ultrasound. The alternative to that would be turning the flashlight on and off, just like we would with a pulsed ultrasound. So there are 2 directions in which we need to consider the intensity. We need to consider it as a spatial consideration. That's looking at the area that the beam is covering, that very intense center, weaker outsides, and we need to look at it over time. Are we looking at the intensity when the flashlight is off? Are we looking at it when it is on? And how long is it on for? Section 5.2, Intensity and Area. As I mentioned, intensity is inversely related to area. If the beam is very concentrated in a small area, the intensity is going to increase. If it's spread out over a larger area, the intensity will decrease. We use the flashlight analogy as an excellent visual for imagining the strong concentrated center area versus the dimmer outer area. But another way we can think about it is a campfire. If you're too far away from the campfire, you're going to feel very little, if any, heat. That's because you're very far away from the fire. There is a lot of area between you and the source. Now, if you move a little bit closer, you're going to start to feel that warmth, and you might find a good, comfortable area in there. There's enough heat, but it's not too intense. However, if you were to get super close to that fire, even put a hand up to it, that heat is going to be so much stronger and more concentrated on your hand, it's going to get way too intense and you're going to pull away. So the area that the energy needs to cover really matters. If you're in a small area, it's going to be very intense. Larger areas become weaker or less intense. When an ultrasound beam leaves the transducer, it has about the width of the transducer. It then focuses towards the center, becoming smaller, and then begins to diverge beyond the focus, becoming wider again. So the area ends up changing from the transducer to the focus and in the distant portion of the sound beam. So this diagram helps to show us that the energy in the sound beam is going to be strongest and most intense at its center. If we look in the circle cross sections of the sound beam, we can see that the orange is representing the more intense area, and that is going to be more centered in the beam. We can see then that the purple is representing the weakening or the less intense area of the cross section, and that's going to be more towards the outside as we get further away from the center and start to increase the area that the beam is covering. And then not only is the beam the most intense at the center of the cross section of the beam, but it's also the most intense at the focus. Again, the focus is where the beam becomes narrowest. It's where the area is reduced the most, which is why we have the most intensity. When we consider how a beam's intensity looks in space, we just need to remember the beam's intensity will vary, be it through the cross-section or down the ultrasound beam. And because of this, 3 things are true. The beam's spatial peak intensity is going to be at the very center of the beam. The beam's spatial peak average is the mathematical center of the intensities of the beam. The spatial peak intensity is stronger than the spatial average intensity. And lastly, the beam has the most intensity at the focus. Let's take a look at this picture a little bit more. The orange in this image is representing the spatial peak. We can see in the cross-section image here that at the very center of the cross-section is the most pure orange area, and that is the spatial peak. That is where we're going to find the most intensity in the cross-sectional area, is at the center of the beam. If we were able to kind of flip this beam on its side and graph the intensity through the edges to the center, we would get something similar to this graph. This is on the outer edge, and this is on the outer edge. As we move towards the center, we'll reach the spatial peak. So again, spatial peak is center of your cross-section, center of your beam, and we can visually see that as the peak of graphed intensities. Now we also have the spatial average, and the spatial average in this image is depicted by the more purple area. Now the spatial average is not the very edge of the beam, and it's not the very center of the beam, but it's the mathematical middle of the intensities found in this beam. Let's say that the center has an intensity of 100 milliwatts per centimeter squared, and that the very outside has an intensity of 30 milliwatts per centimeter squared. To get the average, we would take 100 plus 30, which is 130, and then divide that by 2, because we have 2 data points to divide. So 130 divided by 2 is 65. So we would find the intensity that corresponds with 65 centimeters squared, and that would be our spatial average. So it's not really towards the center, it's not towards the edge, but kind of somewhere in the middle, depending on the intensities found within the cross-section. Looking at our cross-section of the beam graph then, we could, again, figure out the intensities. If this was 30 centimeters squared and this was representing 100 centimeters squared, then we would do that math, and we would be able to correspond on the graph where the spatial average is. So biggest takeaways from this image: spatial peak is going to be found at the very center of the beam. Spatial average is the mathematical middle of the cross-section through the beam. When we are looking at the beam in a cross-section and we take the value for the spatial peak and the value for the spatial average, we can actually compare the two numbers to tell us how uniform that beam is from center to edge. So the beam uniformity ratio, or BUR, is a comparison of the spatial peak intensity and the spatial average intensity. This is another unitless number, and it's going to tell us how consistent or inconsistent the intensities are across the beam. So the beam uniformity ratio, or BUR, is equal to the spatial pulse divided by the spatial average. The beam uniformity ratio actually comes with a lot of synonyms. It's also known as the SPSA factor, the BUC, which stands for beam uniformity coefficient, or BUF, beam uniformity factor. Typically the value is going to be over 1. That is because the spatial peak should always be stronger than the spatial average. On the bottom, I've got a couple examples that we have seen earlier of our cross-sectional beam. The left one has a more orange hue to it all the way through. That's going to be more of a consistent beam. The center spatial peak is going to be much more closer to the spatial average because it's all kind of being represented by the same intensity. That one's going to have a SPSA factor much closer to 1 because, again, the spatial pulse is going to be much more similar to the spatial average. Compare that then to the purple and orange circle on the right, where we have kind of an intense center, which would be our spatial peak. And then our spatial average is actually going to have to take into account a lot more of that purple weaker area, and we're going to have a bigger discrepancy. That circle's intensity is more inconsistent throughout the cross-section of the beam, and we'll see that SPSA factor increase to much more than 1. To give kind of a real-world example of the SPSA factor, we can kind of think about microwaving a meal. If you've ever microwaved something and had really inconsistent temperatures, that's kind of what we're looking at with the SPSA factor. Say you microwave a pot pie, and the center of it is basically just lava, and the outside of it is still frozen. You had really inconsistent heating. You have a very hot center compared to the frozen edges. If you were to take an average temperature in there, the lava temperature center would be much higher than the average because you got to factor in those frozen parts. But if we microwave our pot pie and it's pretty hot in the middle and relatively hot on the edges, we would see that we had more consistent heating because our center temperature would be much closer to the average temperature of the dish. Section 5.3, intensity and time. When we're thinking about pulsed ultrasound, we know that it typically has a very short burst of sound energy followed by a really long off period in which it's listening for echoes to return. The amount of time that the sound energy is present compared to the off time is described by duty factor. And duty factor can range from 0 to 1 or 0% to 100%. So when the machine is off, we know that the duty factor is at 0%. Typically when we're using our 2D imaging in grayscale, the duty factor is less than 1%. So the sound is on for just a small fraction of time. The rest of the time is waiting to receive echoes from that small burst of sound energy. As we change to different ultrasound modes, such as Doppler, the duty factor can increase by a little bit, usually between 1 and 10%, but 90% of the time is still listening or off time. Lastly, we do see 100% when we are using continuous wave ultrasound, and that means that there is constant ultrasound energy entering the body. Up until this point, most of the graphical representations of pulse ultrasound that you have seen has shown very uniform cycles within a pulse. But in reality, the cycles within the pulse vary in amplitude, power, and intensity. Typically, the beginning and the end are a little bit weaker, where the center of the pulse is strongest. So at the center of the pulse is typically where we are going to find the temporal peak, and that is going to be the strongest intensity within the pulse, where the highest power is, where the highest amplitude is. Because of the varying intensities within the pulse, we also need to consider that there is a pulse average. We have some lower intensities, some higher intensities. We will find the mathematical center of those intensities and call it the pulse average. And lastly, we have the temporal average. Now, the temporal average is considered during the on time of the pulse and the off time of the pulse. So we do have intensities found within the on time that we will consider, but when we consider all the time in the off time, remember that had an intensity of 0. So the temporal average tends to be much lower than the temporal peak and the pulse average because it is considering all of that off time. And we'd be able to calculate the temporal average based on multiplying the duty factor by the pulse average. When we look at the continuous waves temporal considerations, remember that duty factor for continuous waves is 100% or 1. If we were to plug that into our equation, 1 multiplied by the pulse average, we're going to see that the pulse average doesn't change. Therefore, pulse average and temporal average are completely the same when using continuous wave ultrasound. And that's completely because there is no off time in the continuous wave. So knowing that the pulse is not uniformly strong, knowing that there is on and off time, we do need to consider that the intensity of the ultrasound beam when using pulse wave is going to change over time. So we need to remember that temporal peak is the strongest intensity. Temporal average ends up being the weakest because it includes the on and off time. And the pulse average is going to be weaker than temporal peak, but stronger than temporal average because it is all of the on time. And when the machine is listening or off, the intensity is going to be at 0. Section 5.4, measuring intensity. Here I've got a couple examples of hydrophones, which are also known as microprobes. And these are tools that can measure the output intensity of a beam that's produced by one of our ultrasound transducers. I have two types of hydrophones imaged here. We have the needle variety, which can be moved around through the beam, and then we have the disc variety that kind of catches all of the information from the beam. The hydrophone is attached to an oscilloscope, and the hydrophone will be able to measure the pulse repetition period, the pulse duration, and the period of the wave. And from these parameters, as we've done in multiple examples in the past, we can actually calculate most of the other parameters of the wave. The hydrophone is capable of measuring amplitude, power, and intensity as well. And we want to know the strengths of the beam because they have a large effect on how the beam will interact with human tissue. That sound on human tissue interaction is known as bioeffects, and we always need to be mindful of this when we are using ultrasound equipment for the patient's safety. Here's an image of a disc hydrophone being used to measure the output from a transducer. All of the equipment is placed into a water, that's why it's a hydrophone, it's a water microphone, and it's going to receive that sound energy from the transducer, display the information on an oscilloscope, and then we'll be able to take data out of there to calculate the parameters that we've discussed. When we are calculating those parameters, though, we need to consider a couple things. Where was the beam measured, and when was the beam measured? Was it measured during a spatial peak or the spatial average? And was it taking information when the wave was at its temporal peak, during its temporal average, or at its pulse average? And because we can measure intensity at any 2 of the spatial considerations and any 3 of the temporal considerations, we can actually combine them together to get a better picture of what is happening. On the next slide, we're going to see a little video that puts all the combinations together. So SP is spatial peak, SA is spatial average. Those are going to be combined with the temporal considerations. TP for temporal peak, TA for temporal average, and PA for pulse average. So when we add spatial peak and temporal peak, we get SPTP, which is the strongest intensity. Next, we have spatial average and temporal peak, spatial peak and pulse average, spatial average and pulse average, spatial peak and temporal average, which is what we want to consider for bioeffects, and lastly, spatial average and temporal average, which is our weakest intensity. Now, I mentioned on the SPTA image that we are concerned about bioeffects when we are looking at the SPTA intensity, the spatial peak temporal average intensity. Ultrasound really has not shown any severe adverse side effects in the application of diagnostic medical sonography. However, we do know that computer studies do suggest that in very strong pulses and for very long durations, we might actually start to see some bioeffects occur. The first type of bioeffect that we are concerned about are mechanical bioeffects. These are typically going to arise when the pulse is very strong. What it ends up doing is causing liquid to form small bubbles, and this is called cavitation. There's an image on the side, a little video, and you can see that it is liquid. Pressure within the liquid causes a bubble, and as that pressure oscillates through the bubble, it can cause the bubble to collapse or burst. And when it does that, it actually has a lot of energy going with it. So the concern is that ultrasound will cause liquid in the body to form tiny little gas bubbles. Those tiny little gas bubbles will rupture, causing cell damage when they do so. 2D ultrasound or grayscale ultrasound is typically going to run the higher risk of causing cavitation, and the SPPA intensity is closely related to the amount of cavitation that will occur with a beam. The other type of bioeffect that we are concerned about are thermal concerns. Now, these are going to arise from a duration of a pulse that interacts with the body. So if we were to hold a beam on one spot for a really long time, there's a bigger chance that the tissue is going to heat up, since the sound energy is going to be partially transferred into heat energy. Doppler is going to be more likely to cause heating in tissue, and that's because the sample area has longer pulses and repeatedly samples the same area. We're putting stronger sound energy directly in the same spot multiple times. Studies have shown that if we increase the area that ultrasound is located in by 2 degrees Celsius, we actually can cause some harm to the tissue. For thermal considerations, we watch the spatial peak temporal average. That's why you need to know that spatial peak temporal average is closely related to bioeffects. The thermal bioeffect is a little bit more concerning than the mechanical, as there's a lot more factors that go into the mechanical cavitation part. The thermal bioeffects are just 100% the intensity of the beam interacting with the tissue and how much heat they can cause. Now, the reason that we use spatial peak and temporal average is because it is a truer representation of how the sound beam is interacting with the human body. They are not just getting the temporal peak, they're not just getting the pulse average, they are getting the on and off time. So we want to make sure that we are considering that there's on and off time, and they're going to be getting all of that central beam intensity, so that doesn't change. Ultrasound machines are not available for public use or purchase. You do need to be a medical provider, school, or veterinarian to purchase a machine, and that is because they are FDA regulated. And with the FDA regulating them, they make sure that the ultrasound machines do not produce an SPTA intensity more than 720 milliwatts per centimeter squared. We'll be covering much more about bioeffects towards the end of this course, but in the meantime, if you're curious about where you can monitor the mechanical and thermal bioeffect, we actually have it right on the screen. Typically up in the corner, you'll see a number preceded by MI, which stands for mechanical indice and TI, which stands for thermal indice. The higher the mechanical indice is, the more likely cavitation is going to occur and the rupture of bubbles, and the TI indicates the degree of temperature in which the ultrasound beam could possibly raise the temperature. So in this example, we could raise the temperature by 0.2 degrees Celsius using the ultrasound beam that we have activated. And that brings us to the end of Unit 5. Now, ultrasound intensities wasn't a very long unit, and that's because a lot of these concepts are a little bit more in the abstract. The biggest things that you need to take away from the intensity unit is that intensity is measured in a watts per centimeter squared, which means that it is directly related to power and inversely related to area. So as the area increases, the intensity should decrease. The ultrasound beam changes in relationship to space, and it changes in relationship to time. So we have two spatial considerations: spatial peak, which is at the center of the beam and is the strongest, and the spatial average, which is the mathematical middle of the intensities in space. Looking at the temporal ones, we have temporal peak, which is the strongest point of the pulse. We have the temporal average, which includes all intensities during the on and off time. And then we have the pulse average, which includes the mathematical average of the intensities found just within the pulse. Taking those 5 intensity measurements, we combine them together to make 6 combination measured intensities. The strongest is the spatial peak, temporal peak. The weakest is the spatial average, temporal average, and we are most concerned with spatial peak, temporal average for bioeffects because it is the truest representation of what our patients experience in relationship to the ultrasound energy.